From space, our planet looks like a smooth blue marble. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. But look closer, and you start to see the edges. The places where the deep blue of the ocean meets the pale brown and gray of the land. That thin, ragged line stretching around every continent and island on Earth. That is the shoreline. And along that shoreline, tucked into the rocks, hidden in plain sight, sits one of the most remarkable places on our planet. The Tidal Pool. It is a small thing. You could step over some of them. You could hold the water of one in your cupped hands. But do not let the size fool you. These little pockets of seawater, carved into coastal rock, hold entire worlds inside them. They are home to creatures that have lived on Earth far longer than we have. They are places where the rules of survival are written fresh every single day. The coastlines of Earth stretch for roughly 620,000 miles. That number is almost impossible to picture. It is long enough to wrap around the planet nearly 25 times. And along much of that distance, wherever you find rocky shores, you find tidal pools. They appear on every continent. They sit along the cold gray coasts of Scotland and the sun-warmed shores of California. They cling to the volcanic rock edges of Hawaii and the ancient sandstone cliffs of Australia. Wherever the ocean reaches up and touches solid ground, tidal pools form. They are born from something very simple. The ocean rises. The ocean falls. It does this twice a day, every day, without stopping. As the water pulls back, it leaves small hollows and basins filled with seawater. The sun beats down. The wind blows across. And yet, life finds a way to stay. Life finds a way to thrive. What makes tidal pools so special is exactly this tension. They sit at the border between two very different worlds. The ocean is cold, deep, and constant. The land is warm, dry, and always changing. A tidal pool is neither one nor the other. It is both. It is a place where creatures must survive the crashing force of waves and the baking heat of a summer afternoon, where the water can turn saltier than the open sea as it evaporates under the sun, where a single storm can flood the whole pool with fresh fresh rainwater and change everything inside it. And yet, life does not just survive here. It fills every surface. It crowds every crack and crevice. The rocks are painted in shades of pink, green, orange, and deep purple from the algae and creatures that coat them. Look into the water, and you might see a sea star, slow and deliberate, moving across the bottom on hundreds of tiny tube feet. You might see a hermit crab dragging its borrowed shell across the sand. You might see a sea anemone, its soft tentacles waving gently in the current, looking more like a flower than an animal. Scientists believe that tidal pools may have played a role in one of the greatest events in the history of life on Earth. Around 375 million years ago, the first animals were beginning to make the slow move from the ocean onto land. Tidal pools, with their mix of wet and dry conditions, may have been training grounds of a kind, places where early creatures first learned to breathe air, to move across solid ground, to survive outside the water. Every time you look into a tidal pool, you may be looking at a place shaped like the ones where that ancient story began. There is something deeply calming about standing at the edge of the sea. The sound of the waves, the smell of salt in the air, the cool mist that rises when a wave breaks against the rocks. People have stood at this edge for as long as people have existed. And long before that, creatures of all kinds gathered here. The shoreline has always been a meeting place, a threshold between one world and another. Tonight, somewhere on Earth, the tide is pulling back right now. The water is retreating down the rocks, slow and steady, leaving behind those small, still pools. The creatures inside them are settling in. The sea stars are resting. The anemones are waiting. The crabs are tucked into their corners. The ocean will return. It always does. And when it comes back, it will bring everything with it again. The ocean does not simply sit still. It breathes. Twice a day, in most places around the world, the sea rises up the rocks and then pulls back down again. This rising and falling is what we call the tide, and the force behind it comes from very far away. The moon is the main driver of Earth's tides. It sits about 239,000 miles from our planet. That is roughly 1,000 times the distance from New York to Los Angeles. Even at that distance, the moon's gravity, its pulling force, reaches all the way to Earth's oceans. It tugs on the water. The side of Earth facing the moon gets pulled toward it, and the water there bulges outward. At the same time, a second bulge forms on the opposite side of Earth. This happens because that far side is actually being pulled less strongly, and the water there lags behind. So at any given moment, there are two bulges of water on opposite sides of the planet. As Earth spins, different parts of the ocean pass through these bulges. When your stretch of coastline moves into a bulge, the water rises. That is high tide. When your coastline moves out of the bulge, the water falls. That is low tide. Most places on Earth experience 2 high tides and 2 low tides every single day. The sun plays a role too. The sun is much larger than the moon, but it is also much farther away, about 93 million miles from Earth. Because of that distance, the sun's tidal pull is only about half as strong as the moon's. But when the sun and moon line up, their forces combine. The tides during these times are called spring tides, and they are the strongest of the month. The water rises higher and falls lower than usual. When the sun and moon are at right angles to each other, their forces partly cancel out. These are called neap tides, and the water moves in a smaller range. The difference between high tide and low tide is called the tidal range. In some places, this range is very small. In the middle of the ocean, the tide may rise and fall only a foot or 2, but near coastlines, especially in bays and inlets, where the shape of the land funnels the water, the range can be enormous. The Bay of Fundy on the eastern coast of Canada holds the record. There, the tidal range can reach over 50 feet. That is about the height of a 5-story building. The water rises and falls that much twice a day, every single day. Most tidal pools sit along coastlines where the tidal range is somewhere in between. A range of 4 to 8 feet is common in rocky intertidal zones, the areas where the sea meets the land and the tide comes and goes. That range is enough to expose the rocks for hours at a time, enough to leave pools behind, enough to create the conditions that make tidal pool life possible. The timing of the tides shifts a little every day because the moon is slowly moving in its orbit around Earth. The tides arrive about 50 minutes later each day than they did the day before. Over the course of a month, the cycle completes itself. The moon makes one full trip around Earth, roughly every 29 and a half days. Tidal pool creatures have lived with this shifting schedule for hundreds of millions of years. Many of them have internal clocks tuned to it. They know, in the way that living things know things without thinking, when the water is coming back. The tides are ancient. Earth has had tides for as long as it has had oceans and a moon. Scientists believe the moon formed about 4.5 billion years ago, likely from a massive collision between early Earth and another large body. In those early days, the moon was much closer to Earth than it is now. The tides back then would have been far more powerful, rising and falling in dramatic surges. Over billions of years, the moon has slowly drifted outward. It moves about an inch and a half farther from Earth every year. The tides have grown gentler as the moon has moved away. So when you watch the water pull back from the rocks and leave those quiet pools behind, you are watching something that has been happening in one form or another for nearly as long as this planet has existed. The rhythm is that old. The pull of the moon on the sea, the rise, the fall, the slow, steady breathing of an ocean that never stops moving. But a tidal pool is not just the tide. The tide alone cannot make one. Something else has to be there first. Something solid. Something shaped just right to catch the water and hold it. That something is rock. Most tidal pools form in rocky coastlines. These are places where hard stone meets the sea. The rock has to be tough enough to resist the constant push and pull of the waves. Softer ground, like sand or mud, simply washes away. It cannot hold a pool. It cannot hold anything for long. But hard rock, the kind that has been here for millions of years, can take that beating and hold its shape. The most common rock you find in tidal pool zones is basalt. Basalt is a dark, dense rock made from cooled lava. When a volcano erupts and its lava flows into the sea, it cools very quickly. It hardens widens into strange, rough shapes, jagged edges, uneven surfaces, natural bowls and crevices pressed into the stone. These shapes are not designed by anything. They are simply what happens when hot liquid rock meets cold seawater, and yet they turn out to be exactly what a tidal pool needs. Granite is another rock you find along tidal coasts. Granite is lighter in color, speckled with flecks of white and gray, and sometimes pink. It is one of the hardest rocks on Earth. It forms deep underground when magma, which is molten rock beneath the surface, cools very slowly over millions of years. Over time, the land above it erodes away. The granite rises. It becomes coastline. Waves begin to work on it. And slowly, over thousands of years, the sea carves it into the shapes that hold pools. This carving is the key. Waves do not just push water. They carry sand and small stones with them. Every wave that crashes against a rocky shore is grinding that rock very slowly, grain by grain. Scientists call this process erosion. It is almost impossibly slow from a human point of view. But the ocean is patient. It has been doing this for billions of years. And over that time, it hollows out small depressions in the rock. It deepens cracks. It smooths some surfaces and roughens others. It creates the shallow basins where water collects when the tide pulls back. Some tidal pools form in cracks called fractures, where the rock has split along natural lines of weakness. Water seeps into these cracks, and over time, the freeze and thaw of seasons, the constant pressure of waves, and the slow chemical reaction between seawater and stone all work together to widen them. A crack becomes a crevice. A crevice becomes a pool. The shape of the coastline matters enormously. A coast that faces the open ocean and receives large, powerful waves will erode differently than a sheltered bay where the water moves gently. Rocky headlands, which are points of land that jut out into the sea, often have some of the richest tidal pool formations. The waves hit them from multiple angles. The erosion is complex. The resulting rock surfaces are full of variety, full of small pockets and ridges and channels that trap water in dozens of different ways. The slope of the rock matters too. A very steep cliff face sheds water quickly. A gently sloping shelf of rock, one that angles down toward the sea at a low grade, holds water beautifully. The pools that form on these sloping shelves can be wide and shallow, almost like stone plates filled with seawater. Others are deeper, tucked into natural hollows, shaded by overhanging rock. Each one is slightly different. Each one ends up hosting a slightly different community of life. It took a long time for the coastlines we see today to reach their current shape. The sea level itself has changed many times over Earth's long history. During ice ages, when enormous amounts of water froze into glaciers on land, sea levels dropped. Coastlines that are now underwater were once exposed. When the ice melted, the sea rose again. These rising and falling seas have shaped and reshaped rocky shores again and again over millions of years. So a tidal pool is the result of deep time and slow forces. Lava that cooled into rock, waves that ground that rock for thousands of years, a sea level that rose and fell across the ages, a moon whose gravity still pulls the water twice a day. All of it working together without plan or intention to create a small hollow in the stone where the ocean leaves a little piece of itself behind. That small hollow in the stone is not just one place. It is several places at once. A tidal pool is divided into zones. Each zone sits at a different height on the rocky shore. Each one gets a different amount of time underwater. And because of that, each one holds a completely different world. Scientists who study these shores have given names to these zones. Understanding them is like learning to read a map of a place you have never been before. The highest zone sits closest to the land. It barely touches the sea. Waves splash it during storms. High tides reach it only sometimes. This is called the splash zone, or sometimes the superlittoral zone, the area just above the reach of regular tides. The word superlittoral simply means above the shore. Life here must survive long stretches without water. The sun bakes the rock. The salt dries on the surface like a crust. Very few living things can handle those conditions, but some do. And the ones that do are remarkable. Below that sits the high tide zone. The ocean covers this area highest tides of the month, but it drains away for long hours in between. Animals and plants here must handle both extremes. They must survive being soaked in cold seawater and then left in open air, sometimes under a hot sun. The creatures that live here have developed slow, careful ways of holding water inside their bodies. They have learned over millions of years of evolution to wait. Farther down the slope comes the middle zone. This area gets covered and uncovered twice each day as the tides rise and fall. It sees the most regular change of any zone. The water comes in, the water goes out, then it comes in again. Life here has settled into that rhythm. The middle zone tends to be the most crowded part of the tidal pool system. More water means more food washing in. More time underwater means more chances to feed and breathe. The lowest zone sits at the bottom of the slope, just at the edge of the sea. It is almost always underwater. Only the lowest tides of the month pull the water back far enough to expose it. This zone stays cool and wet. It never dries out the way the upper zones do. Because of that, it can support more fragile life. Soft creatures that could not survive even an hour in open air can live here safely. This zone is the richest of all. It holds the greatest variety of living things. These 4 zones splash, high, middle, and low, stack on top of each other like quiet shelves on a wall. Each one has its own rules. Each one rewards the creatures that have learned to follow those rules. And the boundaries between them are not sharp lines. They blend into each other. A creature from the middle zone might sometimes wander into the high zone. A plant rooted in the low zone might send its fronds drifting upward into the middle zone when the tide is in. The zones are a guide, not a fence. What makes this structure so striking is how much it mirrors other layered systems on Earth. The ocean itself is divided into zones by depth and light. Forests are divided into layers from the canopy, high above down, to the dark forest floor. Even the atmosphere above us sits in layers, each one with its own temperature and pressure and chemistry. Nature seems to find this pattern again and again. Stack things by how much energy they receive. Let each layer develop its own community. Watch life fill draws this in miniature. In a stretch of rock no wider than a quiet country road, you can walk from one world into another, and then into another. The splash zone at the top, pale and crusted with salt. The high zone below it, dotted with small, tough shells. The middle zone, crowded and alive with color. The low zone at the bottom, dark and cool and rich with soft, delicate things. Each zone shaped by the same moon, the same tides, the same ancient rock, but each one a distinct place with its own cast of creatures. The tidal pool is a small thing. You could cross it in a few steps, but inside it, the same organizing forces that shape whole oceans and whole forests are quietly at work. The same principles that sort the deep sea into layers of darkness and light sort this little pool into zones of wet and dry. Small and large, the universe tends to arrange itself the same way. It finds a gradient. It fills every part of it with life. The splash zone sits at the very top of the tidal pool world. It is the highest point on the rock face, the place where the sea barely reaches. The ocean does not wash over it with every tide. Instead, it gets hit by spray. Waves crash far below, and the mist drifts upward. That fine, salty mist is almost all this zone ever gets. And yet, things live here. To understand how, you have to understand the forces pressing down on every creature in this zone. The sun beats on these rocks without mercy. On a clear summer day, the surface temperature of a dark rock in the splash zone can climb past 130 degrees Fahrenheit. That is hot enough to cook an egg. The rock holds that heat and radiates it outward, turning the immediate air around it into something close to an oven. Then the wind arrives and pulls moisture away. Then the rain comes and washes the salt off. Then the sun returns and bakes everything again. The splash zone is a place of swings. Wild, punishing swings between wet and dry, hot and cold, salty and fresh. These swings are driven by forces that never stop. The sun pours energy down in the form of light and heat. That energy evaporates water, concentrating the salt left behind on the rock surface. In some spots, white salt crystals form a thin crust over the stone, pale and rough to the touch. giving the splash zone only seconds of wetness before the stone is dry again. Radiation plays a quiet role here too. Ultraviolet light, the same invisible energy that burns human skin, strikes the splash zone with full force. There is no water to filter it, no canopy of algae to block it. The creatures here absorb that radiation directly. Over millions of years, life in the splash zone has had to develop ways to handle it, to repair the damage it causes, or to build outer layers that block it entirely. The result of all these forces pressing down at once is a zone that looks, at first glance, almost empty. The rock appears bare, pale gray or tan, with patches of black and dark green. But look closer. That black coating on the rock is not dirt. It is a living thing. Cyanobacteria, some of the oldest forms of life on Earth, form thin, dark films across the stone. They have been doing this for billions of years, long before fish existed, long before the first animal crawled onto land. Cyanobacteria were coating rocks just like these, with thin, dark sheets of life. The splash zone is, in a sense, a living museum. The creatures here use some of the oldest survival strategies on the planet. Periwinkles, small snails no bigger than a marble, move slowly through this zone. They carry their homes with them. Their shells are thick and tightly sealed, built to hold moisture inside even when the air around them is bone dry. When conditions get too harsh, a periwinkle simply closes its shell and waits. It can wait for days. The shell locks out the heat, the salt, and the drying wind. Inside, the animal slows down almost completely, using almost no energy until the next wave spray arrives. This ability to pause life, to slow it down to almost nothing, and then restart it, is one of the great survival tools of the splash zone. The forces here do not allow constant activity. They demand patience. They demand the ability to endure long stretches of hardship in exchange for brief windows of moisture and feeding. What shapes the splash zone, then, is not one force, but the interaction of many. Gravity keeps the water from staying. The sun drives the heat and evaporation. The wind strips away moisture. Radiation damages exposed tissue. And the tides, driven by the moon's pull on the ocean, control coastline has existed. They have sculpted not just the rock, but the living things on it, pushing every species toward the same solution. Be small, be tough, be patient, and hold on. The splash zone is the hardest place in the tidal pool to live. It is also the place where life has had the longest time to practice surviving. And practice, it turns out, has made something very close to perfect. Below the splash zone, the rock changes. The color shifts, the texture shifts, and the rules of survival shift with them. This is the high tide zone. It sits just below that harsh, barely wet strip of the splash zone, and it gets covered by seawater at least once a day, sometimes twice. That regular flooding changes everything. Life here still faces heat, dryness, and salt. But it also gets real water, real immersion, real relief. And that small difference opens the door to a much wider world of living things. The high tide zone is not a large place. On most rocky shores, it spans only a few feet of vertical height. Stand at the water's edge and look up the face of a rock. The distance from the high tide line down to where the water sits at low tide might be no more than 6 or 8 feet on a calm coast. On a shore with strong tides, it might reach 15 or 20 feet. But even on the grandest tidal shores, the entire system of zones, from the splash zone at the top to the low tide zone at the bottom, rarely exceeds 30 feet of vertical rock face. 30 feet. That is about the height of a 3-story building. Inside that thin strip of stone, hundreds of species build their entire lives. Think about what that means in terms of scale. The Pacific Ocean covers more than 60 million square miles. It holds more water than all the other oceans combined. And yet some of the most complex, most densely packed communities of life on the planet exist in a strip of wet rock that a child could climb in 30 seconds. The tidal pool does not need vastness. It needs precision. The animals of the high tide zone are built for that precision. Periwinkle snails, small and round, and no bigger than a marble, move slowly across the rock surface here. Their shells are thick and tightly sealed. When the water pulls away and the sun bears down, a periwinkle simply closes its shell and waits. It can can survive out of water for days. Its body slows. Its needs drop to almost nothing. And when the tide returns, it opens again and begins to graze on the thin film of algae coating the rock. A single periwinkle might travel only a few inches in an entire day, but it has been doing this in one form or another for millions of years. Limpets live here too. A limpet is a snail with a low, cone-shaped shell, and it clings to rock with a muscular foot so powerful that it can resist a force many times its own body weight. Scientists have measured the grip of a limpet and found it can hold on against a pull of about 70 pounds per square inch. That is stronger, pound for pound, than many industrial adhesives. The limpet does not grip out of fear. It grips because the waves in this zone can arrive with tremendous force, and anything that cannot hold on will be swept away. Those waves carry real power. A breaking wave on an exposed rocky coast can strike with a pressure of several hundred pounds per square foot. In storm conditions, that number climbs higher still. The animals of the high tide zone have evolved bodies that meet that force without fighting it. Low profiles, smooth shells, flexible bodies that bend rather than break. A limpet's cone shape deflects the water upward and around it, the same way a pointed roof sheds rain. The design is elegant and it is ancient. Barnacles crowd the high tide zone in enormous numbers. A single square foot of rock can hold hundreds of them, their white shells pressed together so tightly that almost no bare rock shows through. Each barnacle is a small animal living inside a ring of hard plates, and when the tide comes in, it opens those plates and extends feathery legs to sweep food from the water. When the tide goes out, it seals itself shut. It breathes the small pocket of air and moisture trapped inside. It waits. A barnacle can live this way for years, sealed and patient, every creature here has learned, over vast stretches of time, to read it perfectly. Below the high tide zone, the rock changes. The color shifts. The texture shifts. Something alive and layered takes over where bare stone once ruled. This is the middle zone. It sits between the high tide line above and the low tide line below. Twice a day, the sea rises and covers it completely. Twice a day, the sea pulls back and leaves it open to the air and sun. No other part of the tidal pool experiences this kind of back and forth so evenly, so reliably. The middle zone is soaked, then exposed, then soaked again, over and over, in a rhythm as steady as breathing. If you could stand at the edge of the rocks and look down at the middle zone during low tide, the first thing you would notice is the color. It is not gray like bare stone. It is not white like barnacle shells. It is green and brown and rust red and deep purple, all layered together in patches and stripes. Mussels cover enormous stretches of the rock in dense blue-black clusters, their shells pressed together like roof tiles, each one anchored firmly to the stone. Between the mussel beds, thick mats of algae spread out in shades of olive green and dark amber. The rock beneath all of it is almost invisible. Life has claimed every surface. Mussels are one of the great success stories of the middle zone. A single mussel anchors itself to rock using thin, strong threads called byssal threads. These threads are made of protein, and they are remarkably tough. Scientists have studied them closely because they stay strong even when wet, which is something most adhesives, most glues cannot do. The mussel makes these threads itself, spinning them out and pressing them against the rock until they hold. One mussel is held in place by dozens of these threads, pulling in slightly different directions, spreading the force of every wave across many small anchor points instead of one. Mussel beds do more than just cover the rock. They create a whole, small world inside themselves. The spaces between the shells trap moisture and shade. Tiny worms live there. Small crabs hide in the gaps. Snails move slowly through the dark interior of the bed, grazing on whatever they find. A mussel bed is not just a collection of mussels. It is a neighborhood dense and layered, full of creatures that depend on the mussels for shelter, even though the mussels do not notice them at all. The algae of the middle zone adds another layer to this picture. Rockweed is one of the most common plants here. It is a brownish-green seaweed with flat, branching fronds and small round bubbles along its length. Those bubbles are filled with air, and they help the fronds float upright when the tide comes in, lifting them toward the light. When the tide goes out, the rockweed drapes itself over the rocks in thick, wet mats. It holds moisture underneath it. It keeps the rock surface cooler than the open air. Many small animals shelter beneath it during low tide, pressed against the damp stone, waiting for the sea to return. Touch a frond of rockweed, and it feels slick and rubbery. It bends easily. It does not snap or crack. This flexibility is part of how it survives. Waves move through the middle zone with real force, and a rigid plant would break. Rockweed bends with the surge and springs back when the water passes. It has been doing this for a very long time. Fossil evidence suggests that seaweeds similar to modern rockweed existed hundreds of millions of years ago, long before the first fish swam in the sea. The middle zone is also where the ochre sea star, a large, five-armed predator with a rough, bumpy surface in shades of orange, purple, and brown, does much of its hunting. Sea stars move slowly across the mussel beds, prying shells open with steady, patient force. They play a powerful role in shaping the entire zone. When scientists removed sea stars from study areas in the 1960s, mussel populations exploded and crowded out nearly every other species. The middle zone lost most of its variety. When the sea stars returned, the balance came back with them. One animal, moving slowly on hundreds of tiny tube feet, had been holding the whole community together. That is the quiet truth of the middle zone. It looks like a surface. It looks like rock covered in shells and weed. But it is a system, every part connected to every other part, each creature shaping the world around it without any awareness that it is doing so. Below the middle zone, the water gets deeper and stays longer. This is the low tide zone. Of all the zones in a tidal pool, this one is the most sheltered. ocean covers it for most of every day. Only the lowest tides pull the water back far enough to expose it. When that happens, for just a short window of time, you can see a world that is almost never visible. What you find there is unlike anything in the zones above. The colors alone are startling. Deep red algae clings to the rock in wide, flat sheets. Bright purple urchins sit in hollows they have slowly carved into the stone. Pale pink coralline algae, a plant that pulls calcium from the water and builds itself a hard, stony crust, coats the surfaces in soft, rosy layers. The whole zone looks painted. It looks like something from a dream. The low tide zone stays wet almost all the time. That means the creatures living there never have to survive the long dry spells that test the animals higher up. They do not need the thick shells or the tight grip of the barnacles in the splash zone. They do not need to seal themselves shut and wait. Instead, they have evolved for richness, for variety, for a life that is almost, but not quite, fully underwater. Sea urchins are one of the most striking animals here. They are round and spiny, covered in hundreds of thin, sharp spines that move slowly in all directions. Those spines are not just for defense. Urchins use them to walk, pushing themselves along the rock in small, deliberate steps. They also use a set of tiny tube feet, similar to those of a sea star, to grip the surface and pull themselves forward. Underneath the body, hidden from view, is a mouth with 5 small, hard teeth arranged in a circle. This structure is called Aristotle's lantern, named after the ancient Greek thinker who first described it more than 2,000 years ago. With those 5 teeth, an urchin scrapes algae directly off the rock. Over time, some species scrape so hard and so often that they hollow out small pits in the stone itself, creating a snug, protected home. Kelp begins to appear in the low tide zone. Not the towering underwater forests that grow in deeper water offshore, but smaller, younger plants anchored to the rock by a structure called a holdfast. A holdfast looks like a tangle of roots, but it does not absorb water or nutrients the way roots do. It only grips. The kelp feeds through its broad, flat blades, pulling energy from sunlight and nutrients directly from the surrounding water. Even in its smaller form here at the edge, kelp creates shelter. Small fish, shrimp, and tiny crabs hide among its blades when the tide pulls back. Nudibranchs live here too. A nudibranch is a type of sea slug, soft-bodied and without a shell, and it is one of the most visually remarkable animals in any tidal pool. Some are bright orange with white-tipped spines along their backs. Some are deep blue with gold edges. Some look like tiny flowers. Their colors are not random. Many nudibranchs are toxic, and the vivid patterns warn predators to stay away. Others borrow their defenses from their food. Some species eat stinging anemones and store the stinging cells inside their own bodies, using them as weapons without ever producing the venom themselves. The low tide zone also holds brittle stars, which are relatives of sea stars, but far more delicate. Their 5 arms are long and thin, and they move by whipping those arms in quick, snaking motions, rather than the slow glide of a sea star. They tuck themselves under rocks and into crevices, coming out to feed on tiny particles of organic matter drifting through the water. What makes the low tide zone so remarkable is how much life it holds in such a small space. Every rock surface, every crack, every hollow is occupied. Animals stack on top of animals. Plants grow on animals. Animals graze on plants that grow on other animals. The density of life is extraordinary. Scientists have counted dozens of species living within a single square meter of low tide rock. And yet, the whole zone is exposed only rarely. Most of the time it sits quietly underwater, going about its business unseen. The tides reveal it like a curtain pulled briefly aside. You get a glimpse. Then the water returns and it disappears again, carrying on without any need for an audience. There is a rhythm to the tidal pool that goes deeper than the tides themselves. The tides come and go twice a day, but the creatures that live here move to many rhythms at once. Some pulse with the hours, some pulse with the seasons, some pulse with cycles that take years to complete. Life in the tidal pool is not still. It breathes and shifts and turns over and over in patterns that have repeated for millions of years. Take the barnacle, that small, pale cone of shell you see cemented to nearly every rock surface. A barnacle begins its life as a tiny creature drifting freely through open water. It is almost invisible. It floats with the currents for weeks, feeding on even tinier organisms. Then something changes. The barnacle larva, that drifting young form, begins to search. It tests rock surfaces with its body, sensing the texture and chemistry of the stone. When it finds the right spot, it glues itself down with one of the strongest natural adhesives scientists have ever studied. It builds its shell around itself and never moves again. That single creature will spend the rest of its life in one place, opening and closing its shell plates with the rhythm of the waves, reaching out with feathery legs to sweep food from the water. Barnacles do not live alone. They tend to settle near other barnacles. Scientists believe they detect chemical signals left by barnacles already attached to the rock. Those signals say, in effect, this place is good. Come here. And so barnacle colonies grow dense and close, covering rocks in pale gray sheets that crunch softly underfoot if you are not careful where you step. A single barnacle can live for several years. Some species live for more than a decade, clinging to the same patch of rock through thousands of tides. The rhythm of reproduction in tidal pools is its own kind of wonder. Many creatures here time their spawning, their release of eggs, and sperm into the water to match the tides and the moon. Mussels, those dark blue-black shells clustered in thick groups on mid-zone rocks, release their eggs and sperm into the water column during certain tidal cycles. The timing is not random. Evidence suggests that mussels respond to changes in water temperature, light, and the physical force of the waves to coordinate their spawning. Thousands of individuals release at nearly the same moment. The water briefly clouds with life. Fertilized eggs drift away, becoming part of the vast floating community of tiny organisms in the open sea, before some of them eventually return to settle on rock and begin again. Sea urchins follow a similar pattern. Those round, spiny animals that graze on algae in the low and middle zones also spawn in coordinated bursts. One urchin releasing its reproductive cells into the water can trigger its neighbors to do is that vast numbers of fertilized eggs enter the water at once, which improves the odds that at least some will survive to become adults. The seasons shape the tidal pool in ways that are easy to miss if you only visit once. In spring and summer, algae grows thick and green and golden. The pool fills with color. Juvenile fish dart through the shallows. Snails graze actively. The whole community hums with energy. In winter, the picture changes. Some species retreat to deeper water. Growth slows. The pool looks quieter, more spare. But it is not empty. Limpets, those simple cone-shaped grazers, remain active through cold months. They scrape algae from rock surfaces with a ribbon of tiny teeth called a radula, a word that simply means a rasping, tongue-like structure. A single limpet can clear a patch of rock so thoroughly that it becomes its own territory, a bare circle of stone that the limpet returns to again and again. Limpets actually navigate. They wander out to graze during high tide, moving slowly across the rock. Then, as the tide falls, they return to the same spot, the same exact depression in the rock, every single time. Over years, a limpet grinds that depression a little deeper with the edge of its shell, creating a custom fit. The rock and the animal shape each other. The limpet's home scar, as scientists call it, holds a thin film of water when the tide is out. It keeps the animal from drying in the sun. That small hollow in the rock is the difference between life and death. Everything here moves in circles. The tide, the moon, the seasons, the life cycles of creatures too small to see clearly without kneeling down close to the water's edge. The limpet is not alone in its devotion to the rock. All across the tidal pool, creatures have found their own ways to hold on. Holding on is everything here. The waves do not ask permission before they arrive. They crash and pull and crash again. To live in this place, an animal must answer one question above all others. How do you stay? Mussels answer that question with threads. Blue mussels, those dark blue-black shells clustered together in dense groups, attach themselves to rock using what scientists call byssal threads. These are thin, silky strands the mussel makes itself, spinning them out from a small organ near its foot. Each thread is stronger than it looks. A single mussel can produce dozens of them, anchoring itself from multiple angles like a tent staked into the ground. The threads are slightly elastic, which means they stretch a little when a wave hits, rather than snapping all at once. The mussel does not fight the wave. It bends with it just enough and then holds. Mussels rarely live alone. They cluster in beds, pressing against each other, their shells overlapping like shingles on a roof. This closeness is not accidental. A group of mussels holds together better than a single mussel ever could. The whole bed absorbs the force of a wave more evenly than any one animal. Inside a mussel bed, the spaces between shells trap moisture and shade. Tiny creatures, worms and small crabs and juvenile snails, shelter in those gaps. The mussel bed becomes a neighborhood. One animal's way of surviving creates a home for dozens of others. Barnacles take a different approach entirely. A barnacle begins its life as a tiny, free-swimming creature, drifting in the open water. Then it finds a hard surface, touches it with its head, and never moves again. It cements itself down with one of the strongest natural glues known to science. Researchers have studied barnacle cement for decades, trying to understand how it bonds so powerfully to wet rock. The barnacle then builds a small fortress of calcium plates around itself, a white cone that looks almost like a tiny volcano. When the tide is out, the barnacle seals its plates shut to hold moisture inside. When the tide returns, it opens and extends feathery legs called cirri, sweeping the water for tiny particles of food. The barnacle feeds with its feet, reaching out in rhythmic, graceful strokes. A rocky surface covered in barnacles has a texture like rough sandpaper. That texture actually helps other creatures grip the rock too. Algae finds footholds in the spaces between barnacle shells. Small snails crawl across them. The barnacle, by cementing itself down and building its little fortress, changes the surface of the rock in ways that benefit its neighbors. It does not intend this. It simply lives. And in living, it makes the rock more habitable for others. Sea stars, those slow five-armed hunters, also have a remarkable way of holding on. The underside of a sea star is covered sea star moves by extending and retracting these feet in waves, creating a slow, flowing motion across the rock. When a wave hits, the sea star presses down, and all those tiny suctions grip at once. The combined force of hundreds of small holds is enormous. Scientists have measured the holding strength of a sea star and found it can resist forces many times its own body weight. All those small connections working together become something much stronger than any single one could be alone. What is remarkable is how different all these solutions are. The mussel uses threads. The barnacle uses cement. The sea star uses suction. The limpet uses its own body weight and a perfect fit carved into stone. Each creature arrived at its own answer to the same problem, shaped by millions of years of waves and weather. And yet, they all share the same rocky surface, each one occupying a slightly different space, using a slightly different method, living in a way that rarely directly competes with its neighbors. This is what makes the tidal pool so quietly astonishing. It is not just a collection of tough animals. It is a community of different solutions, each one fitting into the gaps left by the others. The mussel bed shelters the worm. The barnacle roughens the rock for the algae. The sea star moves slowly among them all. Every creature here is both a survivor and, without knowing it, a neighbor. The rock holds them all. The tide connects them, and the whole surface of the shore hums with a kind of patient, ancient cooperation that has been going on long before any human eye ever looked down into the water. Some creatures in the tidal pool do not simply hold on. They hide. Camouflage, the ability to blend into the background and become nearly invisible, is one of the oldest survival tools on Earth. And in the tidal pool, it reaches a kind of quiet perfection. The rocks here are covered in patches of red algae, gray barnacles, brown kelp, and pale sand. An animal that can match those colors and textures has a powerful advantage. It can hunt without being seen. It can rest without being eaten. It can simply disappear into the surface of the world. The decorator crab is one of the most remarkable examples of this art. This small crab, found in tidal pools along many of the world's rocky coasts, does something almost unbelievable. It reaches out with its claws and deliberately picks up pieces of algae, sponge, and shell. Then it presses those pieces onto its own body, where tiny hooks on its shell hold them in place. The crab is not doing this by accident. It is actively building a disguise. Scientists have observed decorator crabs choosing materials that match their current surroundings. If moved to a new location, some will redecorate. They pull off the old pieces and replace them with new ones that better match the rocks around them. The decorator crab is not the only creature here that uses its environment as a costume. The kelp crab, a slender green crab found along the Pacific coast of North America, has a body color that almost exactly matches the bright green of sea lettuce. A common algae in tidal pools. When it holds still among the algae, it nearly vanishes. Its thin legs look like algae stems. Its flat body looks like a leaf. It can sit completely motionless for long stretches of time, and a passing predator may look directly at it and see nothing but plants. Flatfish, too, are masters of this kind of stillness. Some species, like the Tidal sculpin, can change the pattern of their skin to match the gravel or sand beneath them. They settle onto the bottom and become part of the floor. Their eyes, which sit high on their heads, keep watching, but their bodies seem to disappear. The sculpin can hold this stillness for a very long time, waiting for a small shrimp or worm to wander too close. What is extraordinary is how fast some of these color changes happen. The Tidal sculpin can shift its skin pattern in just a few seconds. The animal's nervous system sends signals directly to cells in the skin called chromatophores, tiny pouches of color that can expand or contract almost instantly. When they expand, the color shows. When they contract, it fades. The fish does not think about this the way a human thinks about choosing clothes. It happens automatically, driven by what the eyes see and what the brain processes without conscious effort. Camouflage also works in rivers. Some tidal pool creatures are brightly colored not to hide, but to warn. The nudibranch, a soft, shellless sea creature related to snails, comes in colors so vivid they seem almost unreal. Electric orange, deep purple, spotted yellow and black. using bold color as a warning rather than a disguise. It works because predators learn. A fish that bites a bright nudibranch once rarely tries again. So the tidal pool holds both kinds of extreme, the invisible and the unmissable, the creature that vanishes into the rock and the creature that blazes against it. Both are using color as a tool. Both are surviving. They simply chose opposite paths to the same destination. This is one of the quiet wonders of this place. The same small pool of water, the same few square feet of rock, holds animals that have evolved in completely different directions. One hides, one glows, one builds a disguise from scraps, one shifts its skin in seconds, and all of them are here together in the same cool water, under the same pale sky, waiting for the tide to return. The tidal pool rewards patience. It rewards stillness. The longer you look, the more you see. A rock that seemed bare slowly reveals a crab. A patch of algae turns out to have eyes. The pool is full of secrets, and most of them are hiding in plain sight. And then there are the hunters. They move through the tidal pool without rushing. They do not need to rush. The pool is small, and their prey has nowhere to go. Predation here is quiet and close. It happens in inches, not miles. A sea star, that slow, five-armed creature moving across the rock, is one of the most effective hunters in the entire pool. It does not chase. It simply arrives. The sea star hunts mussels, and the way it does this is remarkable. It wraps its arms around a mussel's closed shell and pulls. The mussel pulls back. The two animals hold this tension for a long time, sometimes hours. The mussel is strong, but the sea star is patient. It does not tire the way a mussel tires. It uses hundreds of tiny tube feet, small suction-tipped structures along its underside, to keep a steady, unbroken pull. Eventually, the mussel's shell opens just a crack. That crack is all the sea star needs. It pushes its stomach out through its own mouth, slides it into the shell, and digests the mussel from the inside. The sea star then pulls its stomach back in full. This is how the tidal pool works. Slowly, precisely, without drama. The ochre sea star, a deep purple or orange species, common is what scientists call a keystone predator. A keystone predator is one whose presence shapes the entire community around it. When researchers removed ochre sea stars from tidal pools in the 1960s, something unexpected happened. Mussels took over. They crowded out the algae, the barnacles, the other creatures. The whole pool simplified. Fewer species, less variety. The sea star, by eating mussels, had been keeping space open for everything else. Its hunger was a kind of balance. The tidal pool holds that balance in every direction. Hermit crabs move through the shallows, carrying borrowed shells on their backs. They are scavengers mostly, picking through algae and debris, cleaning the pool of what has died. But they are also prey. A large shore crab or a hungry gull will take a hermit crab if it can. So the hermit crab tucks itself deep into its shell and waits. The shell is not its own. It found it. When it grows too large, it will find another. Scientists have observed hermit crabs forming lines near a newly empty shell, each one slightly larger than the last, waiting to trade up. The smallest crab takes the shell left behind by the next smallest, and so on down the line. It is an orderly exchange, and it happens without any apparent signal or instruction. Snails hunt too, though slowly. The dog whelk, a small spiral-shelled snail found in tidal pools across the North Atlantic, drills through the shells of barnacles and mussels using a structure called a radula. A radula is a ribbon of tiny teeth, like a flexible file, that the snail uses to scrape and bore. It takes hours. The snail presses its radula against the shell, works it back and forth, and slowly opens a hole just wide enough to feed through. The shell of the prey remains intact. Only a small, clean hole reveals what happened. These are the quiet details, the ones that only appear when you slow down and look. Even the algae participates in this web of eating and being eaten. Limpets, those small, cone-shaped creatures that cling so tightly to rock, graze on the thin film of algae that grows across the stone. They follow paths. Studies have shown that limpets return to the same spot on the rock after each feeding trip, wearing a slight groove into the surface over time. Their home scar, as scientists call it, fits the shape of their shell exactly. It is a perfect seal against drying out and against predators. The limpet did not plan this. It simply returned again and again, and the rock remembered. Everything in the tidal pool leaves a mark. The sea star's path across the mussel bed, the whelk's clean hole in a barnacle shell, the limpet's worn groove in the stone. These are the records of small lives, written in rock and shell and algae. The pool is a place of constant, gentle pressure. Everything eats. Everything is eaten. Everything finds a way to hold on just long enough to pass something forward. And the whole system turns, slow as the tide itself, held together by 10,000 small negotiations between creatures that have never once thought about the others they depend on. They simply live, and in living, they keep each other going. When the sun goes down and the last light fades from the sky, the tidal pool does not go quiet. It changes. The creatures that hid during the day begin to move. Octopuses slide out from under ledges. Crabs pick their way across wet rock. Small fish dart between the shadows. The pool at night is a different world, and for most of human history, almost no one knew it existed. People have walked beside the sea for as long as there have been people. Coastal communities around the world gathered shellfish from the rocks for thousands of years. They knew the tides came and went. They knew certain creatures clung to certain places, but knowing a thing is there and understanding how it works are two very different things. For a long time, the tidal pool was simply a place to find food. Its deeper life went unread. The first careful written records of tidal pool creatures came from ancient Greek thinkers. Aristotle, the Greek philosopher who lived around 350 BCE, wrote detailed observations about sea urchins, octopuses, and shellfish. He described their bodies, their behaviors, their habits. He was wrong about many things. He believed, for instance, that some sea creatures formed from mud and sea foam without any parents at all. But he was looking closely, and that mattered. He was one of the first people to treat the small creatures of the shore as worthy of serious study. For many centuries after Aristotle, that careful attention faded. The sea was a place of danger and mystery. Most people people who lived near it were focused on survival, not observation. Sailors tracked currents and winds. Fishermen learned where fish gathered. But the creatures of the rocky shore were largely ignored by those who kept written records. Then, in the 1800s, something shifted. In Britain and across Europe, a deep curiosity about the natural world began to spread. People started collecting shells, pressing seaweed, drawing the animals they found in rock pools. It became a kind of passion. Families would visit the shore with glass jars and notebooks. Scientists began writing popular books about the creatures of the tidal zone, and those books sold widely. One of the most beloved was written by Philip Henry Goss, a British naturalist who spent long hours at the shore in Devon, England, in the 1850s. His writing was careful and warm. He described the colors of anemones, the movement of sea stars, the strange beauty of creatures most people had never thought to notice. His work helped spark what historians sometimes call the Great Victorian rock pooling craze, when tidal pools became a subject of genuine public wonder. Goss also made a serious mistake. He encouraged people to take creatures home and keep them in glass tanks, which he called aquaria. The idea caught on quickly. Soon, collectors were stripping tidal pools bare to stock their home tanks. Whole populations of sea urchins and anemones vanished from stretches of coastline. It was one of the earliest examples of human enthusiasm doing real damage to the very thing it loved. Scientists today still study the slow recovery of some of those Victorian-era pools. At night, though, the pool kept its secrets longer. Early naturalists worked mostly in daylight. The tools for nighttime study were limited. Candles and oil lamps gave poor light near water. It was not until the late 1800s and early 1900s when better lanterns and eventually electric torches became available that researchers began to document what the pool looked like after dark. What they found surprised them. Many creatures that seemed inactive during the day were in fact waiting. Chitons, small armored animals that barely move in sunlight, traveled several inches at night to graze on algae. Brittle stars, which are relatives of sea stars with long, thin arms, emerged from crevices and spread across the rock. Some small fish that rested motionless during the day became active hunters in the dark. The pool had two lives, one visible and one hidden, running in the same water. Modern researchers now use waterproof cameras, infrared light, and careful long-term observation to study tidal pools through the night. What they have found is that the night shift is not just a repeat of the day. Different animals are active. Different feeding patterns emerge. The pool reorganizes itself around the absence of light, the same way it reorganizes itself around the presence of water. It is always adapting, always finding a new arrangement that works. The pool does not rest when the sun goes down. It simply becomes something else. And the scientists who finally stayed to watch learned that the shore gives up its secrets slowly, one careful hour at a time. Sea stars are one of the great surprises of the tidal pool. Most people picture them as simple, slow, almost decorative creatures. Something you might find dried on a shelf. But the living sea star is something far stranger and more capable than it first appears. A sea star has no brain. It has no heart. It has no blood in the way that you or I would understand blood. Instead, it runs on seawater. A sea star pumps seawater through a system of tiny tubes inside its body. That water pressure is what moves its hundreds of small tube feet, each one tipped with a gentle suction cup. The whole animal is powered by the ocean itself, drawn in and pushed out in a slow, steady rhythm. Those tube feet are stronger than they look. A sea star can pull open a mussel, which is a small shellfish that clamps its two shells together with remarkable force. The sea star wraps its arms around the mussel and pulls. It does not pull hard and fast. It pulls slowly, steadily, for a very long time. It can hold that tension for hours. Eventually, the muscles tire. The shell opens just a fraction, and that is enough. The sea star pushes its stomach out through its own mouth, slides it into the tiny gap, and digests the mussel while it is still inside its shell. The sea star eats its meal before it even brings it inside its body. This is one of those facts that takes a moment to settle. The stomach leaves leaves the body. The digestion happens outside. Then the stomach returns. It sounds like something from a dream, but it is simply how a sea star feeds. Nature found a solution, and the solution is strange, and it works. Sea stars can also do something that very few animals can manage. They can regrow lost arms. If a predator grabs one arm and pulls, the sea star can release that arm entirely and crawl away on the remaining four. The lost arm is not wasted. It continues to move on its own for a short time. And given enough time and the right conditions, a single arm with a small piece of the central body attached can regrow into a complete new sea star. One animal becomes two. Scientists have studied this ability, called regeneration, for many years. They believe it is connected to the same cellular processes that allow all animals to heal wounds, just taken much further. There are more than 2,000 species of sea stars found across the world's oceans. They come in colors that seem almost invented. Deep orange, pale lavender, bright crimson, soft gold. Some are the size of a coin. The sunflower sea star, found along the Pacific coast of North America, can grow to nearly 3 feet across and carries up to 24 arms. It is one of the fastest moving sea stars known, capable of covering several feet per minute when hunting. In the tidal pool, it is a significant predator. Sea stars are also deeply connected to the health of the entire pool. Scientists studying tidal pools in the 1960s removed all the sea stars from a section of shoreline to see what would happen. What happened was dramatic. One species of mussel spread rapidly and crowded out nearly everything else. The variety of life in that section dropped sharply. When the sea stars were present, they kept the mussel population in check, which left room for barnacles, algae, worms, and many other creatures to survive. The sea star, it turned out, was holding the whole community in balance. Scientists now use the term keystone species for an animal like this, one whose presence shapes the entire system around it. Remove it, and the system changes completely. This discovery changed how scientists think about ecosystems everywhere, not just tidal pools. It showed that a single species can matter more than its size or number suggests. sea star is not the largest creature in the pool. It is not the most numerous, but it is the one that holds the arrangement together. There is something quietly remarkable about that. A slow, brainless animal with no blood and a stomach that travels outside its body turns out to be the quiet anchor of an entire living world. It does not rush. It does not compete loudly. It simply moves and feeds and holds its place, and in doing so, makes room for everything else around it. The tidal pool keeps offering these moments. The creature that seems simple reveals a depth that takes years of careful watching to understand. And the more you look, the more the pool gives back. Tucked into the cracks and ledges of the tidal pool, there is a creature that looks more like a flower than an animal. The sea anemone sits still, its soft tentacles spread wide, swaying gently in the water. It looks peaceful. It looks almost decorative. But those tentacles are covered in tiny stinging cells, and the anemone is one of the most effective hunters in the pool. Each stinging cell is called a nematocyst, a microscopic coiled thread that fires like a harpoon when touched. The anemone does not chase its prey. It simply waits. A small fish or shrimp brushes against the tentacles. The cells fire, and the prey is paralyzed in an instant. Then the tentacles fold inward, drawing the meal toward the anemone's central mouth. The whole process is slow and quiet. There is no struggle. There is barely any movement at all. What makes the anemone even more remarkable is what it chooses not to sting. The clownfish, a small, bright orange fish with white stripes, lives among the anemone's tentacles without being harmed. Scientists have studied this for decades. The clownfish produces a special coating of mucus on its body, a slippery layer that seems to prevent the stinging cells from firing. The fish can swim freely through the tentacles, resting inside them, sheltering from larger predators. The anemone, in return, benefits too. The clownfish chases away small fish that would otherwise nibble at the anemone's tentacles. It also stirs up the water as it moves, helping bring oxygen and food particles closer to the anemone. Each creature helps the other. Neither could do as well alone. This kind of arrangement, where two different species live closely together and both benefit, is called symbolism. The tidal pool is full of it. Life here does not just compete. It cooperates. It forms quiet agreements written not in words, but in chemistry and behavior, tested over millions of years of slow change. The anemone's relationship with the clownfish is perhaps the most famous, but it is not the only one. Some species of small shrimp also live safely among anemone tentacles. These shrimp, called cleaner shrimp, pick parasites and dead tissue from the anemone's body. The anemone gets cleaned. The shrimp gets a meal and a safe place to live. The same shrimp will sometimes clean fish too, setting up what scientists call cleaning stations, small fixed spots in the pool where fish come and wait to be groomed. A tiny shrimp, no bigger than a fingernail, runs what amounts to a service that larger animals depend on. Anemones themselves are connected to the broader ocean in ways that go far beyond the pool. When an anemone reproduces, it can do so in two ways. It can split itself in half, each piece growing into a full new anemone. Or it can release eggs and sperm into the water, where they drift out with the tide and eventually settle on a new rock somewhere else. Those drifting larvae become part of the plankton, the vast, invisible cloud of tiny life that floats through the ocean. Plankton feeds fish. Fish feed larger animals. The anemone's offspring, too small to see, become part of a chain that reaches far beyond the rocky shore. The anemone also responds to the sun in a way that connects it to the sky above. Many anemones host tiny algae inside their bodies, living cells called zooxanthellae that use sunlight to make food through photosynthesis. The algae share some of that food with the anemone. In return, the anemone provides the algae with shelter and the carbon dioxide they need to grow. When the sun shines into a clear tidal pool, it is not just warming the water. It is feeding the anemone from the inside out. The sun, the algae, the anemone, the clownfish, the cleaner shrimp, the passing tide. All of it moves together in a slow, interlocking rhythm. This is what the tidal pool keeps showing us. Nothing here lives in isolation. Every creature is woven into the lives of others, shaped by forces that reach from the ocean floor to the atmosphere above. The anemone looks like it is simply sitting still, but it is breathing with the help of the sun. It is sheltering a fish. It is being cleaned by a shrimp. It is sending its children out to sea. All at once, quietly, without any apparent effort. The pool is small enough to step across, but the connections inside it reach in every direction, outward and upward, into the open ocean and the open sky. The anemone holds its place on the rock, tentacles drifting, and the whole world moves gently around it. Now, moving through that same still water, something shifts. A shadow crosses the bottom of the pool. Then another. Small legs, quick and deliberate, pick their way across the wet rock. The crab has arrived. Crabs belong to a group of animals called crustaceans, creatures with hard outer shells and jointed legs. They have lived on this planet for an extraordinarily long time. Fossil records show that crabs, or crab-like creatures very close to them, have existed for more than 500 million years. That means crabs were crawling across ancient seafloors long before the first dinosaur ever walked the earth. They have watched entire mountain ranges rise and fall. They have survived mass extinctions that wiped out most life on the planet. And here they are, still moving sideways across a tidal pool, just as their ancestors did in a world we would not recognize. The sideways walk is one of the most familiar things about crabs. It looks almost comical at first, but it is a very smart solution to a real problem. A crab's legs are arranged on the sides of its body, and the joints bend most easily from side to side. Moving sideways lets the crab take long, efficient steps without its legs tangling. A few species of crab can actually walk forward, but for most, the sideways shuffle is simply the most natural way their body moves. It is not strange at all. It is perfect engineering, shaped by hundreds of millions of years of slow change. That shell the crab wears is called an exoskeleton, meaning the skeleton is on the outside of the body rather than the inside. It is made of a tough material called chitin, the same substance found in insect shells and even in some fungi. The exoskeleton protects the crab from predators and from the physical battering of waves and rocks, but it cannot grow. So, as the crab grows larger, it must shed the old shell entirely grow a new one. This process is called molting. For a short time after molting, the crab is soft and completely exposed. It hides in crevices, under rocks, in the darkest corners of the pool, waiting for its new shell to harden. This is one of the most dangerous moments in a crab's life, but it is also the only way the crab can grow. Change, even when it is dangerous, is the only path forward. Crabs are not passive residents of the tidal pool. They are active and curious hunters. Shore crabs and hermit crabs pick through the algae and debris on the pool floor, eating almost anything they find. Dead fish, scraps of seaweed, small snails, even the shed shells of other crabs. This makes them some of the most important cleaners in the pool. Without crabs, organic waste would build up on the rocks and in the water. The crab moves through the pool like a slow, thorough caretaker, keeping the floor clear. Hermit crabs are a particularly wonderful variation on the crab design. Unlike most crabs, hermit crabs do not grow their own hard shells. Instead, they find empty shells left behind by snails and move in. As the hermit crab grows, it must find a larger shell. Sometimes, when the right shell is scarce, groups of hermit crabs will gather and form what scientists call a vacancy chain. One crab finds a new, larger shell. It moves in. Then another crab takes the shell it just left. Then another takes that one. A whole line of crabs, each one moving into the home the previous crab vacated. It is an orderly, cooperative process, and it happens right there in the shallow water of the pool, quiet and unhurried. Crabs are also changing right now in ways that are slow but measurable. As ocean temperatures rise and the chemistry of seawater shifts, crab populations are moving. Some species are appearing in waters farther north than they ever did before. The green crab, a species originally from European shores, has spread across coastlines around the world, carried in the ballast water of ships. In its new homes, it competes with native crabs and disrupts the local balance of the pool. The tidal pool, which has held its rhythms for millions of years, is now adjusting to a faster pace of change. But the crab itself remains what it has always been: patient, armored, adaptable. It has outlasted which looks like an odd choice, but has worked for 500 million years. It sheds its skin to grow. It borrows its home when it needs to. The crab does not resist change. It simply finds the next available shell and moves in. Below the waterline, where the crab has just settled into its borrowed shell, something else is happening. Something quieter still. Something that has no eyes, no shell, no claws. But it is alive, and it is everywhere in the pool, and without it, almost nothing else could survive. Algae. It coats the rocks in sheets of green and gold and deep rust red. It drifts in soft strands through the water. It clings to the sides of shells and the undersides of stones. To a passing glance, it might look like simple slime, like something to wipe away. But algae is one of the oldest and most important living things on this planet. Some forms of algae have been here for more than 1 billion years. They were photosynthesizing, turning sunlight into food, long before any plant ever grew on land. In a tidal pool, algae is the foundation. It is the base of the food chain, the first link in a long and careful sequence. Small creatures eat it. Larger creatures eat those smaller creatures. The whole pool depends on the energy that algae pulls from sunlight and locks into living tissue. Remove the algae, and the pool begins to collapse. It is that simple and that important. Light is what makes all of this possible. Sunlight enters the water and travels downward, but it does not travel equally. Different colors of light reach different depths. Red light fades first, absorbed by the water within just a few feet of the surface. Orange and yellow follow. Blue and green light travel farthest, which is why deep water looks so blue. In a tidal pool, which is shallow, most of the visible spectrum reaches the bottom. This is one reason tidal pools are so rich with color. The algae living there can use a wide range of light wavelengths to grow. Different algae have adapted to use different colors of light. Green algae, which you often see near the surface in bright, sunlit patches, uses the full strength of direct sunlight. It is a vivid, almost electric green, the color of new leaves. Red algae grows deeper, or in shadier corners of the pool, where it catches the blue and violet light that filters down through the water. pigments, the natural chemicals that give it color, are tuned to absorb exactly the light that reaches it. This is not an accident. It is the result of millions of years of slow, careful adaptation. Brown algae, often called kelp in its larger forms, grows in thick, rubbery strands. In tidal pools, smaller relatives of kelp drape themselves over rocks and sway gently when the water moves. They feel almost like leather. Their color is a deep, warm amber, somewhere between brown and gold. And when sunlight hits them at a low angle, they seem to glow from within. Scientists have found that brown algae produces a pigment called fucoxanthin, which helps it capture the green and yellow light that green algae tends to ignore. Each type of algae has found its own slice of the light spectrum to call its own. This is one of the quiet wonders of the tidal pool. Species that might seem to be competing for the same resource have instead divided it up. They share the light without conflict, each one tuned to a different frequency, like instruments in an orchestra, playing separate parts that together make something whole. Algae also does something remarkable for the water around it. During daylight hours, algae releases oxygen as a byproduct of photosynthesis. A healthy tidal pool full of algae and bathed in sunlight produces a steady stream of tiny oxygen bubbles. You can sometimes see them rising from the rocks in the afternoon, small and silver, catching the light as they drift upward. The pool is breathing. At night, the process reverses. Without sunlight, algae cannot photosynthesize. Instead, like all living things, it consumes oxygen as it carries out basic life functions. The oxygen level in the pool drops slightly in the dark hours. By morning, when the sun returns and the algae begins to work again, the balance is restored. The pool moves through this cycle every single day, inhaling and exhaling with the light. Coralline algae, a type that absorbs calcium from the seawater and builds a hard, chalky shell around itself, does something even more lasting. It cements loose rocks and shell fragments together, slowly building up the solid structure of the pool itself. It is pink and pale lavender, delicate looking but extraordinarily tough. It helps create the very walls that shelter the creatures living inside them. is not just feeding the pool. In some places, it is building it. And then the tide pulls away. It happens slowly at first. The water retreats in long, quiet sheets, sliding back over the rocks with a soft hiss. That sound, the thin whisper of receding water over stone, is one of the most peaceful sounds on earth. It is the sound of the ocean letting go, just for a little while. When the tide goes out, the tidal pool is left behind, and it becomes a different kind of place. The roar of the open sea fades into the distance. What remains is something much quieter, something almost still, but still is not the same as silent. Lean close to a tidal pool at low tide, and you will hear it breathing. Small bubbles rise and pop at the surface, each one making the faintest tick against the air. This is the algae, still working, still releasing oxygen into the water. The sound is so soft it barely registers, but it is there, steady and constant, like a slow heartbeat. The creatures of the pool make sounds too. Limpets, those small, cone-shaped animals that grip the rock like tiny helmets, move across the surface with a faint scraping sound as their muscular foot drags against stone. It is almost too quiet to hear without pressing your ear very close. But in the hush of low tide, with the sea pulled back and the wind calm, that small scrape carries. Snails leave a similar trace of sound as they graze across algae-covered rock. The sea urchin, moving on its hundreds of tiny tube feet, makes almost no sound at all. It drifts across the pool floor like a slow, dark thought. But the spines of a sea urchin, when they brush against rock or shell, produce a faint, dry clicking. Scientists studying urchins in quiet tanks have recorded this sound. It is barely there, but it is real. The most dramatic sound in a tidal pool at low tide comes from the mussels. Mussels cluster together in thick, dark groups, their shells pressed tightly against one another. When the water level drops and the air temperature changes, their shells shift slightly. They expand and contract with the heat. And as they do, they produce a soft, irregular crackling, like the sound of a fire settling. A large mussel bed at low tide on a warm afternoon can produce this sound continuously, a quiet chorus of small adjustments. Hermit crabs add their own percussion, borrowed shells across rock and gravel, producing a low, irregular scraping. When two hermit crabs meet and one attempts to claim the other's shell, the encounter involves a rapid, rhythmic tapping as each crab knocks against the other's shell to assess its size and strength. Researchers have studied this behavior closely. The tapping is not random. It carries information. The crabs are, in their way, communicating through sound. Water itself makes sound inside the pool. When a wave pushes water into a narrow crack in the rock, the air trapped inside is forced out with a sharp exhale, almost like a breath. These small blowholes, scattered across rocky shores, produce irregular puffs and sighs as the surf moves in and out. From a distance, a rocky shoreline at low tide sounds like something quietly breathing, in and out, with no particular urgency. Even the rock itself is not silent. Basalt and granite, the hard volcanic and crystalline stones that form many tidal pool shores, expand slightly in the heat of the afternoon sun and contract again as evening cools the air. This thermal movement, though invisible, produces faint cracking sounds deep in the stone. The rock is responding to the same daily cycle that governs everything else in this place. Heat and cold, light and dark, the tide going out and the tide coming back. Sound travels differently in water than it does in air. In water, sound moves nearly 5 times faster. The creatures of the low tide zone, still submerged even when the pool is exposed, live in a world where every vibration carries quickly and clearly. A fish moving through the pool sends pressure, waves through the water that other animals can detect without hearing in any way we would recognize. The lateral line, a row of pressure-sensitive cells running along the sides of many fish, picks up these waves the way an ear picks up sound in air. The pool is full of signals that no human ear could ever catch. The tidal pool at low tide is not a quiet place. It only seems that way. Underneath the stillness, there is a constant, layered conversation happening between rock and water, shell and stone, creature and creature. Everything is listening. Everything is responding. The ocean waits just offshore, ready to return. change. And the numbers behind that change are simple, elegant, and a little astonishing. Seawater, on average, contains about 35 grams of salt for every liter of water. Scientists call this salinity. That ratio, 35 parts salt to every 1,000 parts water, stays remarkably steady across most of the open ocean. The deep sea holds to that number the way a clock holds to its rhythm. But inside a tidal pool, that number can shift dramatically in just a few hours. When the sun beats down on a shallow pool, water evaporates. It lifts right off the surface and disappears into the air. The salt, though, stays behind. It has nowhere to go. So as the water level drops, the salt becomes more and more concentrated. A pool that started the day at normal ocean salinity might climb to twice that level by afternoon. The water thickens, in a sense. It becomes a stronger, saltier solution than anything the open ocean would ever produce. The creatures living in that pool must handle this shift without leaving. A small periwinkle snail, no bigger than your thumbnail, seals itself inside its shell and waits. Its body slows down. It pulls inward. It can survive salinity levels that would kill most ocean animals outright. The math of survival for a creature like that is written in patience and in the thickness of its shell. Rain works in the opposite direction. A sudden summer storm can flood a tidal pool with fresh water in minutes. The salinity crashes downward. For animals built for salt, this is just as dangerous as too much of it. Some species can tolerate a wide range. Scientists call this being euryhaline, meaning they can live in waters of many different salt levels. Others are far more sensitive. A small shift of even a few grams per liter can be enough to end them. The pool sorts its residents by this tolerance, quietly and without mercy. Temperature follows its own set of numbers. The surface of a tidal pool exposed at midday in summer can reach 35 degrees Celsius. That is 95 degrees Fahrenheit. The open ocean nearby might sit at 15 degrees Celsius. That is a difference of 20 degrees across just a few meters of distance. For the animals in the pool, that gap is the difference between their world and the world just outside it. They live in the hotter, harsher version, and they have adapted to do exactly that. Some algae in tidal pools produce special proteins that help them function at high temperatures. These proteins act like tiny stabilizers, keeping the algae's internal chemistry working even when the water feels almost warm to the touch. The same principle appears in organisms living near deep-sea vents, in hot springs, in desert soils. Life finds the same elegant solution in very different places. The chemistry is different, but the logic is the same. Oxygen levels in the pool also shift with temperature. Warm water holds less dissolved oxygen than cold water. As the pool heats up through the day, the oxygen available to fish and crabs and worms quietly decreases. Some animals respond by slowing their movements. Others move to the shaded edges of the pool, where the rock keeps the water slightly cooler. A few can absorb oxygen directly through their skin when the water level drops low enough to expose them to air. Each solution is precise. Each one is the result of millions of years of small adjustments. The pH of the water, a measure of how acidic or basic it is, also swings inside a tidal pool in ways the open ocean never experiences. Photosynthesis by algae and sea grasses during daylight hours pulls carbon dioxide out of the water, raising the pH at night. When photosynthesis stops and respiration takes over, carbon dioxide builds back up and the pH drops again. The pool cycles through this chemical rhythm every single day. Some researchers study tidal pools specifically because of this. The pools act as natural laboratories, running experiments in chemistry that the rest of the ocean runs far more slowly. All of these numbers, salinity, temperature, oxygen, pH, move together in a kind of quiet coordination. Change one, and the others shift in response. The pool is not a still, simple puddle. It is a system of interlocking forces, each one tuned to the others, each one running on rules that are ancient and exact. The animals living there did not choose these conditions. They were shaped by them slowly over vast stretches of time until they fit the numbers perfectly. And yet, for all that precision, the tidal pool is is not just a place where creatures survive. It is a place where new life begins. Many fish species that live in the open ocean return to tidal pools to lay their eggs. The rocky walls and sheltered corners offer something the open sea cannot: protection. Out in deep water, eggs drift freely and are eaten by countless predators. But tucked into a crevice in a tidal pool, wedged beneath a ledge slick with algae, a cluster of eggs has a fighting chance. The pool holds them close. It keeps them still. The woolly sculpin, a small fish found along the Pacific coast, lays its eggs in the mid-tide zone and then guards them fiercely. The male fans the eggs with his fins to keep oxygen moving through the water around them. He does this for weeks. He barely eats. The eggs are pale and small, pressed together in a tight mass against the rock. Without that constant fanning, without that steady current of fresh water washing over them, they would not survive. The pool makes it possible. The fish makes it possible. Each one depends on the other. Tidal pools also serve as nurseries for young crabs, urchins, and sea stars. These animals begin their lives as tiny larvae, microscopic drifting creatures that look almost nothing like their parents. The larvae float in the plankton, carried by currents, until something draws them down to the rock. Scientists believe that chemical signals released by adult animals, and even by the rock itself, help guide the larvae toward good settling spots. The young animals sense these signals and respond. They sink. They attach. They begin to grow. This process is called larval settlement, and it is one of the most important events in the life of a tidal pool. If the conditions are wrong, if the water is too warm, too acidic, or too low in oxygen, the larvae may not settle at all. They drift past. The pool goes without new recruits. Over time, if this happens repeatedly, the population of a species can collapse. The pool does not recover quickly. Some species take years to return. This is what makes the tidal pool so fragile. It is not fragile in the way a piece of glass is fragile. It is fragile in the way a conversation is fragile. One wrong word, one missing piece, and the whole thing falls apart. Every species in the pool is connected to several others. Remove one, and the effects ripple outward in ways that are hard to predict. was once the top predator of the mid-tide zone. It ate mussels, keeping their population in check. When a disease swept through sea star populations in the 2010s and killed them in enormous numbers, the mussels spread unchecked. They crowded out other species: barnacles, algae, small invertebrates. All of them lost ground. The pool changed shape, not physically, but ecologically. The web of relationships shifted because one thread had been cut. Scientists call a species like the ochre sea star a keystone species, an animal whose presence holds the whole system together the way a keystone holds an arch. Take out the keystone, and the arch falls. The tidal pool, for all its toughness, rests on these invisible supports. What is remarkable is how long this system has held. Tidal pools have existed for hundreds of millions of years. The specific species have changed as the planet has changed, but the structure, the zones, the cycles, the web of predator and prey has persisted through ice ages, through shifts in sea level, through the slow drift of continents. Life found a way to organize itself in this narrow strip between land and sea, and it has kept that organization running across deep time. There is something quietly astonishing about that. The conditions required for a tidal pool to function are precise. The tides must move in a regular rhythm. The rock must be hard enough to hold. The water must carry the right chemistry. The sun must warm the pool without cooking it. The air must be breathable. The planet must sit at just the right distance from its star to allow liquid water to exist at all. Every one of those conditions is met every single day on thousands of coastlines around the world. The pool fills, the pool drains, the eggs hatch, the larvae settle, the sea star hunts, the mussel holds on, and somewhere in a crevice barely visible, a new generation clings to the rock and waits for the tide to return. And yet, for all we know about tidal pools, the ocean keeps its secrets. Scientists have studied these rocky shelves for more than 200 years. They have cataloged thousands of species. They have mapped the zones, traced the food webs, measured the temperatures, and watched the tides roll in and out across countless seasons. And still, there are questions that remain open. Still, there are things happening larvae find their way home. When a barnacle or a sea urchin releases its young into the open ocean, those tiny creatures drift for weeks. The currents carry them far from shore. They float in the dark water, barely visible, smaller than a grain of rice. And then, somehow, they return. They settle back onto rocky coastlines. They find the right zone, the right surface, the right community of creatures. Scientists know that some larvae sense chemical signals in the water, traces left by adults of their own species. Some may respond to light or to the sound of waves breaking against rock, but the full picture is still unclear. How a creature with no brain, no eyes, and no map navigates hundreds of miles of open ocean and lands in roughly the right place is one of the quiet wonders that researchers are still working to explain. There is also the question of how tidal pool communities recover after disaster. A large wave can scour a pool clean, stripping away years of growth in a single surge. A heat wave can cook the upper zones, killing thousands of animals in a matter of hours. After events like these, life returns. The algae grows back. The barnacles settle. The mussels spread across the rock again. But the order in which species return and the reasons why some communities rebuild quickly while others struggle is not fully understood. Scientists call this process succession, the slow re-establishment of a living community after disturbance. In tidal pools, succession can take years, and the end result is not always the same as what was there before. The forces that guide which species arrive first and which ones follow remain an active area of study. The deep connections between tidal pools and the open ocean are also still being mapped. A tidal pool is not a closed system. It breathes with the sea. Every high tide brings in new water, new nutrients, new larvae, new energy. Every low tide sends organic matter back out into the ocean. Tiny pieces of algae and animal waste that feed creatures far from shore. Scientists believe that tidal pools may play a larger role in coastal food webs than their small size suggests. The nutrients that cycle through these pools may support fish populations, seabirds, and even marine mammals that never come close to the rocks themselves. But measuring that contribution precisely is difficult. is still being traced. There is also much we do not know about how tidal pool creatures experience their world. Do sea anemones sense pain when they are disturbed? Do hermit crabs make choices or simply respond to chemical signals? Do the small fish that dart through the pools have any awareness of the space they inhabit? These are hard questions to answer, and scientists approach them carefully. Evidence suggests that some invertebrates, animals without backbones, respond to harmful stimuli in ways that look like pain responses. But whether that response involves anything like experience is a question that biology and philosophy have not yet settled together. And then there is the largest open question of all. How many species remain undiscovered? New creatures are still being found in tidal pools every year. Many of them are tiny, living in the thin film of water between grains of sand, or tucked into crevices so small that a human fingernail could not fit inside. Scientists call these miniature hidden animals myofauna, and they suspect that thousands of species in this size range have never been formally identified. The tools for finding them are improving. DNA sampling of seawater can now detect the presence of a species from the traces it leaves behind, without ever seeing the animal itself. This technique, called environmental DNA analysis, is opening new doors. Researchers are finding evidence of creatures they did not know were there. The tidal pool, this small and ancient place, is still giving up its secrets slowly. It has been studied for generations, and it is still not fully known. That is not a failure of science. It is an invitation. The rock is patient. The tide will keep returning, and there is still so much left to find. The tidal pool has always been a kind of mirror. It reflects the health of the ocean. It reflects the state of the climate. And right now, it is reflecting something that scientists are watching very closely. The ocean is warming. Over the past century, average sea surface temperatures have risen by about 1 degree Celsius. That may sound small, but for creatures living in tidal pools, even a single degree can shift everything. The animals and plants in these pools are already living at the edge of what they can survive. A warmer tide means warmer water the sea pulls back. Some species can adapt, others cannot. Mussels, for example, are sensitive to heat in ways that are easy to measure. When air temperatures rise above a certain point, mussels on exposed rock can overheat and die in large numbers. Scientists have documented mass die-offs along the California coast during heat waves. These events leave bare patches on the rock where dense mussel beds once grew. The bare rock takes years to recover, and during that time, the whole community that depended on the mussels shifts and changes. Sea stars have faced their own crisis. A disease called sea star wasting syndrome spread along the Pacific coast of North America beginning around 2013. It killed sea stars by the millions. Without sea stars to control their numbers, mussel and urchin populations exploded. Kelp forests declined. The ripple moved outward from the tidal pool into the deeper ocean. One animal, gone from one small zone, changed the shape of an entire coastline ecosystem. Ocean acidification is another force reshaping these pools. The ocean absorbs carbon dioxide from the air. As carbon dioxide levels rise, the water becomes more acidic. This makes it harder for animals to build shells and hard skeletons. Barnacles, mussels, sea urchins, and corals all rely on calcium carbonate to build their protective structures. In more acidic water, those structures dissolve faster than they form. Scientists have already measured this effect in tidal pool animals along multiple coastlines. The shells are thinner. The growth is slower. And yet, the tidal pool is not simply a place of loss. It is also a place of remarkable resilience. Some algae species actually grow faster in warmer, more acidic water. Some animals are shifting their ranges, moving toward cooler waters near the poles. New communities are forming in places that were once too cold to support them. The pool is changing, but it is not empty. Life finds its footing. Over a much longer span of time, the picture grows stranger and more vast. In roughly 500 million years, the continents will have moved again. The Atlantic Ocean may close. New mountain ranges will rise where ocean floors once sat. The shorelines of today will not exist. The tidal pools clinging these particular rocks will be long gone, replaced by others on shores we cannot yet imagine. The rock remembers nothing. The tide does not mourn. In about 5 billion years, the sun will begin to expand into what astronomers call a red giant. It will grow so large that it may swallow the inner planets entirely. The oceans will boil away long before that. The tidal pools and every living thing that ever clung to their rocks will be gone, but the atoms will remain. The calcium from a barnacle shell, the iron in a sea star's blood, the carbon in a strand of algae, all of it will scatter back into space. Some of it may eventually drift into a new solar system, forming somewhere else. Some of it may become part of a new ocean, on a new world, circling a younger star. That is not a sad thought. It is a patient one. The universe has always worked this way. It builds, and it scatters, and it builds again. The tidal pool is one small chapter in that long, slow story. It is a place where the sea and the land have been in conversation for hundreds of millions of years, where life learned to survive the in-between, where creatures no bigger than a grain of rice have found ways to hold on through heat and cold and pounding waves. What tidal pools tell us about Earth is this: the planet is always in motion, always adjusting, always finding a new balance after each disruption. The rock erodes, the species shift, the climate changes, and still, when the tide comes back in, something is there to meet it. The pool fills again. The anemones open. The small crabs move sideways across the wet stone, and the whole quiet world begins once more. People have been drawn to tidal pools for a very long time. Long before scientists had names for the creatures inside them, coastal people around the world were crouching at the water's edge, looking in. They were fishing, gathering food, reading the tides. They were watching. There is something in us that responds to the tidal pool, something ancient and quiet that recognizes it, even if we cannot say why. For thousands of years, coastal communities built their lives around the rhythm of the tides. The people of the Pacific Northwest harvested mussels and sea urchins from rocky shores. Communities along the coasts of Ireland, Japan, and Chile read the tides the way others read the sky. curiosity. It was a pantry, a calendar, a clock. The ocean gave, and the people received, and they learned to give back by not taking too much. That relationship between people and tidal pools has shaped science in ways that are easy to overlook. Some of the earliest careful observations in marine biology came from people simply sitting beside pools and writing down what they saw. In the 1800s, naturalists in Britain began visiting rocky shores with notebooks and hand lenses. They sketched anemones. They measured the zones. They noticed that certain creatures only appeared in certain places. That careful, patient watching built the foundation of what we now call ecology, the study of how living things relate to each other and to their environment. One of the most beloved of those early naturalists was a woman named Philip Henry Goss, and later, writers like Anne Pratt and others who brought tidal pool science into homes across Britain through popular books. Their writings sparked what historians call a pteridomania for the sea, a wave of public fascination with marine life that filled Victorian parlors with glass tanks and pressed seaweed collections. Ordinary people fell in love with the tidal pool. That love eventually helped build the case for protecting coastlines from overharvesting and pollution. Today, scientists still use tidal pools as outdoor laboratories because the zones are so clearly defined, and because the creatures are easy to observe. Pools offer a rare window into how ecosystems respond to change. Researchers have studied the same pools for decades, tracking shifts in species as ocean temperatures rise. What they find in those small rocky basins tells them things about the larger ocean that no satellite can show. The tidal pool is a measuring tool, a mirror held up to the health of the sea. And then there is the other kind of knowing, the kind that does not come from a notebook. Many people carry a tidal pool memory somewhere inside them. A childhood afternoon on a rocky beach, the cold shock of the water, the strange thrill of finding a sea star tucked beneath a ledge. The way time seemed to slow down while you watched a hermit crab drag its borrowed shell across the sand. Those moments leave a mark. Scientists have found that spending time near the ocean, even briefly, lowers stress hormones in the body and quiets the nervous system. The sound of moving water, the smell of salt air, the cool mist on the skin, all of it signals something deep in the human body that says, you are safe, you are home. That feeling makes sense when you consider where we came from. Life began in the sea. Every animal on land, including every human being, carries the ocean inside them. Our blood is salty. The fluid around our cells shares a chemical similarity with seawater. Our embryos, in their earliest days, pass through stages that echo the ancient forms of sea creatures. We did not leave the ocean entirely. We carry it with us. So when a person crouches beside a tidal pool and feels something stir, something they cannot quite name, that feeling has a long history. It reaches back past childhood, past human memory, past the first footsteps on land. It reaches all the way back to the edge of the ancient sea, where life first learned to breathe air and feel the sun. The tidal pool is not just a place we visit. It is a place we remember in some part of ourselves that is older than language. We are made of the same elements as the creatures in those pools. The same calcium, the same carbon, the same iron that colors our blood once drifted through the cores of distant stars. We are not separate from the tidal pool. We are related to it. We are part of the same long, slow unfolding that began in the dark water and has never really stopped. The tide goes out. The tide comes back. And somewhere in that rhythm, we recognize ourselves. The tide goes out. The tide comes back. It has done this for longer than any creature on Earth has been alive to watch it. Right now, somewhere on this planet, a wave is pulling back from a rocky shore. It leaves behind a shallow pool, glittering in whatever light the sky is offering. Maybe it is the gold of late afternoon. Maybe it is the pale silver of a full moon. The pool sits quietly, holding its small world together, waiting for the sea to return. It always returns. The moon is roughly 239,000 miles from Earth. That distance changes slightly as the moon follows its oval-shaped path around us. When the moon swings a little closer, its gravity pulls a little harder on the ocean. The tides grow slightly taller. The pools fill a little deeper. When the moon oceans as we know them today. There is something deeply calming in that number. 4.5 billion years of tides, long before the first fish, long before the first shell, long before anything crawled onto land and looked back at the water it came from. The rhythm was already there, steady as a heartbeat, patient as stone. Scientists have found ancient rocks called tidal rhythmites, which are layers of sediment laid down by tides hundreds of millions of years ago. These rocks hold a record of old tidal cycles pressed into their layers like the rings of a tree. By reading them, researchers have learned that the moon was once much closer to Earth. The tides were stronger then. The days were shorter. The planet spun faster. Over billions of years, the moon has slowly drifted outward, and Earth's spin has gradually slowed. The tides themselves helped cause this. The friction of all that moving water pulled back and forth across the ocean floor has gently braked our planet's rotation over deep time. The tidal pool, in this way, is part of a conversation between Earth and Moon that has shaped the very length of our days. And still, the tide comes back. Think of what that pool has seen in the long stretch of time. It has seen the continents drift. It has seen mountains rise and wear away. It has seen ice sheets cover the poles and then retreat. It has seen creatures evolve, grow complex, and spread across the land. Through all of it, the water kept moving. The moon kept pulling. The shore kept receiving the sea over and over in the same ancient exchange. Tonight, the ocean rests under a wide sky. The stars are out. The Milky Way, our galaxy, is a soft smear of light above the water. That galaxy holds somewhere between 100 and 400 billion stars, and it turns slowly. One full rotation taking roughly 225 million years. Our solar system rides along inside it, moving through space at about 515,000 miles per hour. We are always in motion, even in stillness, even in sleep. And yet the tidal pool is quiet. The anemones have drawn their petals in. The hermit crab has tucked itself into its shell. The sea stars rest against the rock, their arms spread wide, their bodies slowly breathing through the water around them. The tiny fish hover in the dark corners of the pool, still and calm, waiting for morning. The water holds them. The rock holds the water. The earth holds the rock. The sun holds the earth in its warm, steady pull. And the whole turning system holds all of us. Every creature, every pool, every wave, in something so large and so gentle that we rarely have words for it. You are part of that system. Right now, as you rest, your body is made of atoms that have been part of this planet for billions of years. The calcium in your bones was once part of ancient seabeds. The water in your cells has cycled through clouds, rivers, and oceans more times than anyone can count. You are not separate from the tidal pool, or the ocean, or the turning galaxy above it. You are woven into the same long, slow story. The tide goes out. The tide comes back. Somewhere right now, a small pool fills with cool, clear water. A wave retreats. The shore glistens. The moon hangs above it, all patient and bright, doing what it has always done. And the world rests. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.